So I'm happy to introduce our next speaker, Qing Zhang from Purdue University, that will tell us about modular categories with transitive Galois actions. Thank you, Qing.
Thank you, Julia. Thanks for the organizers, Julia and Monique, for this chance to talk. And it's great to see everyone here. Last Friday, Andrew gave a nice talk with the topic of doubly rational finite groups, where he mentioned about the Galois actions on the S matrix of modular tensor categories. The modular categories in his talk have integer entries of the S matrices. So all the simple objects are fixed by the Galois action. Today, I'm going to talk about kind of like the opposite extreme case of this action. In other words, the case that when the Galois action is transitive. This talk is based on a paper on ICAF. It is a joint work with Richard Ng at LSU and Yilong Wang. Yilong was a postdoc at LSU, and he will be moving to Sichuan University in China for the next semester. So we consider modular categories with modular data S and T. Here we use capital S and T for and normalized modular data. The entries of S and T have certain restrictions. For example, by Wi-Fi's theorem, the order of the diagonal matrix D is finite. So the entries of T are roots of unity living in certain cyclotomic field. It is also interesting to look at the number field obtained by rational Q adjoining all the entries of S. In the study of rational conformal field theory, De Boer and Gorik considered the Galois extension of Q with all entries of the S matrix. They showed that the Galois group of this extension is always abelian. The Kronig-Weber theorem states that any finite abelian extension of Q is contained in the cyclotomic field. So just like the T matrix, the entries of S also live in a cyclotomic field. In 2010, Ng and Schoenberg showed that for any modular tensor category, the entries of S are contained in the nth cyclotomic field, where n is the order of the T matrix. The Galois theory is used in the classification of modular categories by rank. Here, rank means the number of simple objects in the category. For example, they are used in the classification of rank 4, which was done by Rowell, Stone, and Wang, and also in the classification of rank 5 by Bluyard, Ng, Rowell, and Wang. Roughly speaking, to obtain a classification of modular tensor categories at certain rank, one needs to consider, start from looking at the abelian subgroups of the symmetric group SR, where R is the rank of the category. Then for each case of the abelian subgroup, one determines the corresponding possible modular categories. So motivated by this process, we ask the following question. Can we classify modular categories by the number of the orbit? At the first step towards answering this question, we look at the extreme case when the orbit is 1. In other words, the Galois action is transitive, which is the topic of today's talk. So this is our motivation for this project. In the following, I will talk about the SL2Z representation for a modular category, which Harry mentioned earlier in his talk. This is an essential tool for our topic. Then I will talk about Galois actions on the entries of S with some examples, which Andrew already mentioned that last Friday. For the second half of this talk, we will see what are the consequences if we restrict the Galois action to be transitive. So every modular tensor category gives a projective representation of the special linear group SL2Z. More specifically, this comes from the fact that for any modular category, the S and T matrix satisfy the following relations. Well, S to the power of 4 is the square of the global dimension times the identity matrix. And ST cubed equals to P plus times S squared. Well, this P plus is the Gauss sum Henry mentioned earlier. It's the summation over the simple object by taking the product of the twist and the dimension square for each simple object. The group SL2Z can be generated by the following two metrics. Sorry. Well, S is the off diagonal and T is upper triangular. The generators satisfy the following relation. So by sending the generators of SL2Z to the modular data as S and T, this gives a projective representation of SL2Z. This projective representation can be lifted to linear representations. In this talk, we will be focusing on the following lifting. We consider the normalized S by dividing the positive square root of the global dimension, and the normalized T by dividing a complex number gamma, where gamma is any third root of the multiplicative central charge. After the normalization, we get a linear representation of SL2Z, which we will call it rho. This representation plays an important role in our project. It was proved by Dong, Lin, and Yin. This representation has kernel a congruent subgroup of level n, where n is the order of the normalized T. As a consequence, the image of this representation factors through the finite group SL2Z mod n. Also, the image of rho sits inside of the general linear group GLR, where R is the rank of the category, and this general linear group is defined over the cyclotomic field of degree n. So the entries of S and T are in this cyclotomic field of order n. So from now on, we will denote the Galois group of Q adjoining the entries of S by GC. Let K0 be the fusion ring of a category C. If the category is modular, there is a one-to-one correspondence between the simple objects of C and the characters of the fusion ring. For each simple object Y, the character chi of Y sends every X to this ratio SXY over S1Y. This is a ring homomorphism from the fusion ring to the complex numbers. And all the chi of Y, where Y runs through the simple object, these are the set of linearly independent characters for the fusion ring. Therefore, for any element sigma in the Galois group GC, we have some permutation of sigma hat on the set of simple objects, such that sigma acting on this ratio SXY over S1Y, this is equal to sigma hat acting on the simple object Y. So, this describes the Galois action on the modular tensor category, which Andrew mentioned last Friday. So let's look at a concrete example about this. Let's consider the easy modular category. It is a rank 3 modular category with S matrix like this. So if we rewrite the S matrix in terms of this ratio, we have the following form. So, and the Q adjoining the entries of S is Q adjoining square root of 2. And the Galois group is isomorphic to Z2. By looking at this second matrix, we know that the second simple object is fixed by the Galois action, and the non-trivial element in this Galois group interchange the first and the third simple object. So this is actually a non-example of the type of category we want to focus on today, which we want the action to be transitive. With this background, we're ready to talk about modular categories with transitive Galois action. We say a modular category is transitive if the Galois group acts transitively on the set of simple objects. Our first non-trivial example is the Fibonacci category. It is a rank 2 category with 2 simple objects labeled by 1 and tau. The fusion row is generated by tau tensor itself equals to 1 plus tau. And the S matrix of this Fibonacci category is like this. And consider the S entries in the form of this ratio. And as you can see that Q adjoining the entries of S is Q adjoining square root of 5. And the Galois group is isomorphic to Z2, and it's generated by the element that sends square root of 5 to its Galois conjugate. So it is a transitive category, and one observation we have here is that the order of the Galois group is of order 2, which is the same as the rank of the category. In fact, this is in general true. For transitive modular category, the rank is the same as the order of the Galois group. We show that if the category C is transitive, then the order of the Galois group is the same as the rank of the category. This result is based on the fact that the Galois group is an abelian group, and the transitive abelian group action is also fixed point free. Therefore, G acts on the set of simple objects freely and transitively. In particular, we have the order of the Galois group is the same as the rank of the category. So this is our first observation of transitive modular categories. With this result, we can uniquely identify a simple object in the category with the element in the Galois group, which leads to a list of useful results. This proposition is also useful as a quick criterion to check if the category is transitive or not. Recall that Ising category has Galois group of order 2 and rank 3, so it's not transitive. Another example is the following Deligne tensor product of 2 Fibonacci categories. Up to permutation of the entries as the S matrix is just the chronic product of the original ones. Therefore, the Galois extension of this category is Q adjoining square root of 5. So the Galois group is of order 2. However, the rank of this new category, Fib tensor Fib, is the rank of this category is 4, which is not equal to the order of the Galois group. So Fibonacci tensor itself is not transitive. Okay. So one question to ask here is that when is the Deligne tensor product of 2 modular categories transitive? The answer is the following. The tensor product of modular category C and D is transitive if and only if both of them are transitive. And we have this intersection of this 2-field extension, which obtained by Q adjoining the dimension of C and Q adjoining dimension of D is trivial. This is actually a corollary of a result I will talk about in the next slide. So our question reduces to figuring out the prime transitive modular categories. So we say a modular category is prime if every modular subcategory is equal to itself or the trivial one. And the Muger's theorem states that every modular category is equivalent to a finite Deligne tensor product of the prime ones. But the factorization may not be unique. There's one case that we know that the factorization is unique. Davidoff, Muger, Nikšić, and Austrich show that if the pointed subcategory is trivial, then the factorization of modular tensor category is unique up to permutation of factors. Well, this C pointed is just the maximal pointed subcategory generated by the invertible simple objects. It turns out transitive modular tensor categories satisfy this property, and therefore their prime factorization is unique. More precisely, we have the following. If C is a transitive modular category, then every fusion subcategory is a transitive modular subcategory, and the prime factorization is unique up to permutation of factors. The first result is based on the fact that we show that every fusion subcategory of transitive modular categories is modular, and we further show that it's also transitive. And the second result is based on the observation that the pointed part of transitive modular category is trivial. So to understand transitive modular categories, we need to figure out the prime ones. So what are those prime transitive modular categories? So starting from rank 2 Fibonacci category, by looking for more examples while increasing the rank, we found a class of examples that coming from the quantum group category SU2 at certain level. These are actually adjoint subcategories of SU2 at level P-2. So let's first take a look at SU2 at level P-2. These are quantum group categories from the representation of a quantum group SL2 at 2pth root of unity, while P is greater than 3 and it's a prime. It has P-1 simple object labeled from 0 to P-2. The object X1 is a generating object, and this is an example of fusion rho of tensoring with S1. However, this is not a transitive category since the object labeled by P-2 is an invertible object. And the transitivity implies that there's no non-trivial invertible object. So the category SU2 at level P-2 is not transitive. Now we consider its subcategory by throwing away this pointed one. So these are the adjoint subcategory of SU2 at level P-2, and we call them PSU2 level P-2. When P equals to 5, this is the Fibonacci category. The simple objects are those from SU2 level P-2 with even labels. And this is an example of the fusion rho of tensoring with S2. And the entries of the S and T are given as follows. Well, the entries of S are given by the quantum integers in terms of the indices. And the T matrix is given in terms of the root Q. This category is transitive, since if we take this ratio Sij over S0j, we get the following quantum integer. To show that it is transitive, it suffices to show that for every j, it is in the object of the object labeled by 0, the trivial object. So using the fact that P is the prime and 2J is coprime to 2P, we know that there's always an element in the Galois group that sends 0 to J. So it is transitive. It is also a prime category. This comes from the fact that every non-trivial simple object in this category tensor generates the whole category. And if we change the root Q by another primitive two-piece root of unity, we get another category. And we will call it a Galois conjugate of PSU2 at level P-2. An important fact about these categories is given by the following theorem by Ferrari and Curler, which states that if C is a modular category that has the same fusion role as this category PSU2 at level P-2, then C is equivalent to a Galois conjugate of this category. So we use this theorem in proving one of our main results, which I will state later in the next slide. So this is a list of examples of prime and transitive modular categories, which are just the PSU2 level P-2 and their Galois conjugate. And it turns out these are all of them. To show this, we need the following observation. If a modular category C is transitive, then recall the linear modular representation we mentioned earlier. This rho is irreducible. So why is this result is important? As we mentioned earlier, for any modular category, the representation rho factors through the finite group SL2Z mod n. And using the Chinese remainder theorem, we can reduce to the case when n is equal to a prime power. And the irreducible representations of SL2Z mod p power, prime power are classified in the literature. Therefore, by showing that this rho is irreducible, we can reduce our question to some known result. So combining this and the previous theorem about PSU2 level P-2 by Fourier and Curler, on the previous page, we were able to show this following result. If C is a non-trivial prime transitive modular category, then C is equivalent to a Galois conjugate of PSU2 level P-2 for some prime P greater than 3 as modular categories. So these are all the prime transitive modular categories. Putting this together with the unique factorization, we were able to show our final result of transitive modular categories. That is, if C is a non-trivial transitive modular category, then C is equivalent to a Deligne product of prime transitive modular categories with their T order distinct. And that's all I want to talk about today. Thank you.